Hey guys, I hope everybody's had a good week. I don't know what time of the day or night that you may be watching this, but this is going to be the recording for Chapter 2, the structure of the atom. There seems to be a lot of information in this chapter, but there's not as much that you will have to memorize. I want you to especially look at some of the things that I'll go over today with you, okay? But this one won't take very long. Again, like the others that I've done, these objectives are coming from the textbook. These are not what's in your module itself. This chapter in the textbook is going to discuss atomic theory. We're going to talk about the nature and structure of the atom, the constituents of the atom and the characteristics, the different classifications of the atom, and then the principal types of atomic bonding. So, the focus of it itself is the structure and nature of the atom and knowing what that is, and that it is an atom that we are actually X-raying when we talk about the images that we obtain. Now there's going to be in this chapter a brief history of the development of the theory that traces the progression of it, of the atom and how it was discovered, and then the classification of them as it relates to the periodic chart, okay? But all of this is important for our overall knowledge base to begin with. So, you're probably going, what has the atom got to do with actually knowing about X-ray? Well, it's very important in our education and training as a radiography student because the interactions in the X-ray tube that produce X-rays are at the atomic level, and the nature of the X-ray photon produced depends on how an electron interacts with an atom. So we will learn the components of an atom, and they include the photon, the neutron, and the electron, and it's how they're produced and then how it interacts is very, very important. The second thing is that interactions between those X-ray photons and a human body also occur at the atomic level. They are determined by the radiation dose that is delivered, and what was that? Rad, and then how the body part will be imaged. Third, the interactions between the X-ray photons exiting the patient, so what hits the patient and then exits is also interacting at the atomic level to generate the final image. So what actually creates the image is the radiation that we want, but then there's going to be some scatter radiation that will also interact at the atomic level. So it is very important. Finally, other areas of study in the radiologic sciences require working a knowledge of the atom, and so it's best to develop a strong foundation right now. So when you get towards the end and you start looking at some of the other modalities of imaging, this will become very important for you, okay? So let's go over the history. Even though it's all in your book, you can read it. This is just a little short historical overview. Some people believe that the atomic theory actually goes all the way back, and it goes before this gentleman. I don't know how you would say it. I'm going to say Leucippus, but that can be taken any way you want, but he's most often associated with the early atomic theory. His ideas were vague, and it's his student, Democritus of Abdera, who is the one that's credited for giving the more detailed and elaborate theories. Now, you have to understand, Democritus lived about 460 BC to about 370 BC. Now, BC means before the birth of Christ, so that's even before 0000. So just think about it's as far back as that we actually credit this theory. And then the name itself of an atom comes from a Greek word called atomos or atomus, however it is that you want to say that right there. The Greek word means indivisible. So Democritus hypothesized that all things were made of tiny indivisible structures called atoms, and he believed these atoms were indestructible. So not only could they not be divided, but they couldn't be destroyed. He also said that they all differ in their size, their shape, and their structure, and he said that the nature of the object depended on its atoms. His explanation, and again, this was a very long time ago, sweet things were made of smooth atoms, bitter things were sharp atoms, solid things consisted of small pointy atoms, and liquid things were large round atoms. So that's where this little detail comes in right here. The four elements that we think about back in the day when scientists were first working on what are we made out of, everything relates back to water, earth, air, and fire. So that's what he also based his information on. So all of this has been debated, carried forward another 2,000 years, and then eventually we started getting other scientists that started working on these theories. So our later scientists that we may have actually heard about at some point, the first one is John Dalton. Now, I know you could probably care less about how the man looked, but I always like throwing their pictures up there just in case. So he was an English chemist in the early 1800s, and he developed an atomic theory based not on philosophical, which is what those other guys were, but this is on scientific evidence. He recognized that elements combined in definite proportions formed a compound, and he wanted to know why that happened. So then that and his thinking and his questions turned to his atomic theory. To explain the phenomenon, he theorized that all elements were composed of tiny, indivisible, and indestructible particles called atoms. Okay, we've heard that one before. Every atom is unique to each element in the size and mass of that atom. From that, he decided that compounds were formed by molecules, and molecules are fixed ratios of each type of atom. Therefore, it resulted in a predictable mass. So if you knew the element that something was made out of, you could determine what type of mass it had. And when we get further into the chapter, you're going to see, if something's a gas, it doesn't have a lot of mass, but then if it's a heavy metal, it does have a large. So, even though his theory is over 200 years old now, it's pretty much still what we base all of our scientific evidence on. Now, we do know that we can destroy the atom through nuclear reactions. So we did disprove that one theory that he had, but at the same time, his basic ideas were correct. So everything starts at the atom level, then they build together to make a molecule, which then makes an element, then you put those together and make compounds. And then these little things right here, this is a picture in your textbook if you've looked at that. These are actually wooden models of the atom. So he made these wooden little circles, and he says each one of these is an atom, and you put them together. But that's a really cool thing that he did that. After John Dalton made his discovery and his scientific theories published, then Dmitri Mendeleev, he advanced Dalton's work by organizing them into the periodic table. Now, that's a picture of him in his later years sitting on a periodic table, and I just thought that picture was really cool because it gives you an idea of who did that. Now, when he actually put this together, he did it in a way where he arranged elements in order of increasing atomic mass and having similar properties. This is very similar to what that we still carry today, but you need to understand when he did it, there weren't as many elements out there. So there weren't as many. He presented this first table. It didn't look like that, of course, but in 1869 to the Russian Chemical Society. And in that, he said that the dependence between the properties of these weights of elements, he described their chemical components, and it was according to their weight and valency. Valency is like the electron valence that it has. And he said he actually made several important points, and it's including the periodic law, and that they're ordered according to their weights, certain properties. And this particular table is what we are still using today, even though we've added to it a whole lot more. Then the next scientist that we had is Joseph John or J.J. Thomson. He discovered the electron in 1897. Okay, y'all get that? 1895 is when who? Wilhelm Conrad Röntgen actually discovered X-ray. So Thomson discovered the electron in 1897. So this was a little bit after it. He discovered something even smaller than an atom. It was a particle so minuscule, but it had a negative charge. He said that the atom is composed of electrons surrounded by a soup, soup that you drink, of positive charge to balance the electrons' negative charges. And he put it like charged plums that surrounded it, and it called it a pudding, and that's why it's now called the plum pudding model. So it's supposed to look like a plum with some electrons kind of spread around in there. And that's what this is right here. This is like a little example of his theory. Now, he actually, this discovery resulted from the fascination with, guess what? The cathode ray tube. So here's a cathode ray tube right here, and it was because everybody else was playing with this tube that he did, and that's when he found the fact that there were some other currents going through the cathode ray tube, and he called it a glowing stream. He said no one knew what that stream was, and after he watched it for a while, he realized that it was attracted to a positively charged electrode. Through his investigation, he theorized that the glowing particles were negatively charged pieces of atoms, and that's where they then took the name and called them electrons. And based on his understanding, like I said, that goes back to how they got the name of it looked like raisins in a plum pudding, and that's why it's called the plum pudding model. So another scientist that you kind of want to know about. Then after that, after Thomson, there came a gentleman named Ernest Rutherford. He was a student of Thomson, and he took his information and went further with it. Rutherford was conducting some scattering experiments by taking a very thin sheet of gold and throwing alpha particles at it. Now, again, we're going to talk about later the electromagnetic spectrum and where alpha particles sit, but I still say play with it in the scientific lab. I know he wasn't really playing, he was experimenting, but he found that alpha particles are made of 2 protons and 2 neutrons, which is basically the nucleus of a helium atom, and they have a positive charge. He put a zinc sulfide screen in a ring around the gold sheet, and so you can see it in this picture right here. Here's his little piece of gold foil, and then here's his sheet of zinc that he put around it, zinc sulfide, and then observed the experiment with the movable microscope. He observed that most particles went straight through the sheet, but some were deflected at varying angles, from slight to all the way to 180 degrees back to where they came from. So he suggested that there were tiny spaces or holes at the atomic level, and those spaces allowed most of the particles to pass through, but some of them hit parts of the atom. So he contradicted his teacher's model and proposed a little bit different variation of it, and he assembled it to resemble our solar system. So he took a positively charged, dense nucleus with little tiny electrons that orbited it, and then from that it explained how some of the particles, the alpha particles, could pass right through the gold sheet. And then his version was radically new, but it did not explain a couple of other physical principles. So he took what his teacher, JJ, had talked about and then put it together into another little model, and then we got just a little bit further. But just so you know, Ernest Rutherford is considered the father of nuclear physics. So he was the first to work with alpha particles in there. After that, we had Niels Bohr. And so I'm sure if you've had any type of science, it doesn't even have to be a physics course, you've probably heard about the Bohr model, and that's named after Niels. He was a Danish physicist who in 1913 he took Rutherford's work and then proposed another theory about the hydrogen atom. And he did that based on quantum theory that energy is transferred in certain well-defined quantities. Now, if you go out there and look for Niels Bohr's image, you will find him a lot of times sitting around with Albert Einstein, and I think that's pretty cool. So they kind of worked together when they were trying to figure this stuff out. So with his theory, he said that electrons move around the nucleus, but only in prescribed orbits. When they jump from one orbit to another, then there's a little bit of quantum light that was emitted. His theory explained why atoms emitted light in a fixed wavelength. The atom is considered the basic building block of matter, so we've all come to that same conclusion. Then Bohr took this theory and said there are three fundamental particles of an atom, and those are electrons, neutrons, and protons. And the quantity of each is unique to the matter or element it composes. So a hydrogen atom is different from lead, and a lead atom is different from tungsten, and go on with every element that we have. In radiology, we select elements for their use because of their structure and how they interact with X-rays. So this just kind of gives us the idea of why it's important when we discuss X-ray in general, that it is important to know the basic physics of it. So you will need to know a little bit more about the protons, neutrons, and electrons and what they actually do. And it's just these simple things about them, okay? So don't get upset that you have to know how that model right there in front of you works. That's not it. So how is the atom made up? I've already said the atom is the building block of matter, and it's the properties of a chemical element. They're very small, but most of the atom is actually empty space. The atom has a nucleus that's made up of protons and neutrons. So right here is the nucleus of an atom. And what I want you to understand, so say this whole thing is an atom. Now it's too small to just see with the naked eye. But right in the nucleus, positive is a proton with nothing there. It's a neutron is neutral. And then what orbits this nucleus are electrons, and they are negative. And right here in the nucleus, if you put these two together, the protons and the neutrons, they are sometimes called nucleons. So they put them to, into another one word. The nucleus is very small and dense, and they're the lightest charged particles in nature. The protons are positive, neutrons, neutral, no charge, and then those electrons that are defined by energy levels and the distance from the nucleus. So every element has a certain amount of electrons, and how many they have that are going around it is part of making up how they name that element. So electrons are always attracted to any positive charge because of the electric force, and then in an atom, that force binds the electrons to the nucleus. That binding energy is what keeps it together and helps the natural tendency for like charges to repel. So you hear some of the words that I'm saying here: protons positive and electrons negative. Different properties means that they attract one another, and if it was both positive, then they repel. So think about two magnets, and so a magnet has a positive side and a negative side. If you try to put the two positive sides together, they won't go, but if you flip one of them over to the negative, then they smack together. So the electrons are constantly orbiting. Wish you could see me. I'm taking my finger now and doing it in a round circle. They're orbiting the shells around the nucleus at a high velocity. That force is the electron binding energy that keeps everything together. The closer the electron shell is to the nucleus, the stronger the binding energy, and the harder it is to knock an electron out of its shell. The further away the shells are, the easier it is to knock it out. Now, right now we're not going to get into the X-ray part of it, but I'm going to tell you, hint, hint, that when it comes to how X-rays are made, the process of X-ray knocking an electron out of its shell is part of the process of what creates that X-ray. It's also what helps us create the image of our patient, and it's what can actually damage people that are standing around it, which we shouldn't be. So all of those things are very important. Now here's another chart, and I believe this is also in your text. So here's what you need to know about it, is that a proton is positive, a neutron is neutral, and then an electron is negative. Now, what's very, very important right here is let's look at these masses. Now, the 1 doesn't really matter. The 1.673 and the 1.675, those are basically the same because of this. They are both at a negative 27, so that is below the 1. So this is a very, very light number. Now, the electron is a 9, so if you only look at that number, you think that the mass of the electron is more, but you would be wrong, because you need to come over here to the negative 31, and that means it's even further to the left of 0, and the further left of the 0 means it's even lighter. It has less mass. So earlier I said the electron is the lightest particle, and the fact that they move very fast around the orbiting is what keeps them light. So you don't have to remember that these numbers, but know that a proton and a neutron are similar in mass, but that the electron is much less mass. In fact, from 27 to 31 is 4/10. So, I mean, that's a lot of difference, even though they're all still very, very small. Okay, so know that, and know also that compared to the mass of the nucleus, electron has very little mass, yet it moves very fast, and that's what makes it have significant kinetic energy to keep up its binding energy force. That was a mouthful, sorry about that. But that's what you need to know about the proton, neutron, and electron. Positive, neutral, negative, and that the electron is the lightest of them all. Here's a little bit more that you need to know. Electrical charge is a characteristic of matter, whether it's a subatomic particle, an atom, or a large object. Doesn't matter. Every proton has 1 unit of positive charge. Every electron has a unit of negative. Neutrons are neutral. They have no charge. And when we talk about charge, yes, this kind of goes back to electricity. So if it's charged or not makes a difference. If an atom has an equal number of protons and electrons, then the atom has no net charge. And I should have written that right here, N-E-T, no net charge, okay, if they're equal. And that means that they can't cancel each other out, and that's a good thing. If that balance is disrupted, though, then if the atom becomes positive, that means there's more protons, or if it becomes negatives, there's more electrons. Because the protons are generally very strong in the nucleus, the cause of the electric charge usually involves the gain or the loss of the electron. Now again, that's very important, because when it comes to X-ray production, like I said before, it is that electron disturbance that actually creates either the X-ray or anything else that's going on. What will also be interesting, I'm not saying it's required, but know that if it's a negative ion or an anion, then it has an extra electron. If it's a positive, then it's a cation, and it's an extra proton. So when we talked about the tube last week, and we talked about the anode and cathode, that should give you an idea too. So something that's positive being thrown at a negative, and it's those negative electrons that can move that creates X-ray production. So, moving on. With the nucleus, it's held together by a strong nuclear force creating a binding energy. And so just know what that binding energy means. It creates a very strong attraction in the nucleus that overcomes even the natural tendency for like charges to repel. And that's a law of electrostatics. Like charges repel, opposites attract. So here's a cute little thing about it. So two things that are alike, they're going to repel, both two negatives, two positives, but if you have oppositely charged, they attract and they'll stick together. That's called law of electrostatics. And this is what holds the protons and neutrons together to form the nucleus. The mass of the nucleus is always less than the sum of the masses of nucleons. And then the difference in mass is the mass defect. It represents the energy necessary to hold them together. Now, all of this comes back to energy, Einstein's equation of E equals mc squared, and that's what's holding that nucleus together. The binding energy is also a measure of the amount of energy necessary to split an atom. If a particle strikes the nucleus with energy equal to the nucleus's binding energy, then the atom could break apart, and that force is referred to as nuclear binding energy and expressed in megavolts. So that's something else that you need to realize, that it's very, very important whether or not it has enough force for nuclear reaction, okay? Then we have electrons. The electrons orbit the nucleus at very high velocities, and they force attraction between the negative electrons and positive protons, keeping them in orbit. So it's that binding energy that's making them move. They're moving so fast. It's not like something we see, but it's there. Just as neutrons and protons are held together in the nucleus by nuclear binding energy, the electrons are held in their orbits by electron binding energy. That energy depends on how close it is to the nucleus and how many protons are in the atom. The closer the electron is to the nucleus, the stronger the binding energy, and that is expressed in electron volts as a little e, big V, okay? Now, with X-ray, and we're going to talk about this in chapter 6, but just so you know, this is what we're leading up to. Knowing how the atom is made, here's the nucleus. We're going to talk about in just a second about these shells that come out like this, but we have something called characteristic X-ray and Bremsstrahlung. So don't worry about those until we get to chapter 6, but what it means is when we have an X-ray that hits one of these electrons and throws it out, then that's a type of X-ray. Then this one does not make it eject. It actually changed the nature of this one because then it moved in. So we'll talk about those later, okay? So don't worry about the characteristic and Bremsstrahlung right now, but we will talk about that in chapter 6. But we do need to know about these electron shells. So electrons do not all occupy the same orbit at the same distance. It has a defined energy level, and everyone is at a different distance from the nucleus. These energy levels are called electron shells and describe a sphere. So you're going to pretend like there's an actual sphere, but it probably relates more to like this. Here's the nucleus, and then there's the electrons coming around. But we draw them like this so that we can see where they actually are. So electrons orbit three-dimensionally around the nucleus. They're not simply orbiting in a single plane, because as this orbits right here inside the shell, the whole thing's moving back and forth too. And so I'm sure you can imagine how that looks when it's moving. You see these little lines right here? So as it's running through these lines, it's also moving around, but it's just staying in that same area. So right here is an electron shells and how they're defined. This one is a first shell, so this would be a hydrogen atom because it's low on the chemical element chart. The lithium has some in just one in the second shell, and then lithium has 3 electrons in 2 shells. So it just depends on how many electrons are there and how far away from the nucleus they are. So our next thing is to talk about these orbital shells. You'll see this a lot too. Now this is an argon, so there's 18, and that means there should be 18 of these. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, there's your 18 right there. And what you need to know about these electrons is that they do not all occupy the same orbit. and I've already said they're three-dimensionally. Every shell starting from the nucleus going out, so starting the very middle, the very first shell is called the K shell. K for Kellogg. Oh, well, there it is right there. And then they fill from here outward. And so they go in alphabetical order. And I have no idea. I remember asking the same question. Why do we start with K? Do not know. But it goes K, L, M, and then of course if you have more, N, O, P. I guess you could go all the way out to S and, wherever you wanted to go. But they fill from the K shell outward, with the outermost not filling completely, depending on the stability and nature of the atom. Each shell has a limit to the number of electrons that it can hold. Never, ever, ever will you have more than 2 in the K shell. And so if an atom has 3 electrons, 2 are going to be in the K, then 1 in the L. So an easy way to determine the maximum number of electrons that will fit in a shell is the formula right here, 2n squared. So with the shell's number is 1, L is 2, M is 3, and so on. And what that means is, so 1 squared is 2. But the L shell could be 2 squared, so that'd be 4. So it just goes on from there. Each one of them can have multiple, but there's a certain number. Do you need to know exactly how many are in each one? No, not at this time. But this is here to tell you that an argon element has 18, never more than 2 right here, and there's never more than 8 in the outermost, and that's called the octet rule. And it says that even though a shell can hold more than that, they're not necessarily full, but a maximum of 8 can exist in the outermost shell. So if they could have one more shell and then have more elements out there, but once you reach 8, then you can't go any further. So, but the M shell can contain 18 electrons. So we have KLM. But if that's the outer shell, you can't put 18 there. You would have to have done, say this was a 20. Well, then 2 of them have to go somewhere else. So these are the rules about your orbital shells. K is the closest to the nucleus. They go in alphabetical order. You can never have more than 2 in K, and you can never have more than 8 in the outermost, whatever that outermost is. If it's Q, then it cannot have more than 8. So always just those little simple rules is the only thing that you need to know about them. You do need to know too, though, that an atom has targets, and think of that just like you have an archery. So pretend like these are the lines that you're shooting an arrow at. So here, let's go to K, there's no more than 2. So then right here, look at that. There's more than 4 in here, and that's okay. But they just keep going out and out and out, and then here's the one out here. So this is actually tungsten, and that's just the way that it's made. And there's a greater opportunity for interactions with large, complex atoms because the nucleus is larger. There's more electron shells and more electrons in orbit. There's lesser opportunity for interactions when it's a small, less complex atom because the nucleus is smaller. Now, what that would mean is that if you were using the archery technique or the analogy of that, you can actually hit something that is 3 feet away and instead of 3 feet in diameter than one that is 3 inches in diameter. So look at this right here. If you're aiming and you want to hit something out here, look how much bigger space than you have for this one right in the middle. So the bigger the more electrons and the more shells that it has, then there's more likely going to be an interaction out there. So when it comes down to the chart itself, let's talk about classification. Before we start talking about classification and bonding, you need to understand a few definitions, and one of those is the atomic number. The atomic number of an atom refers to the number of protons that it has in its nucleus. So if it's a stable atom, then the number of electrons is equal to the number of protons, so that atomic number also indicates the number of electrons. Remember, every element is unique. The other definition is an atomic mass number. So here's your atomic number, and it's represented by Z. But when we look at these charts in a minute, that whatever that number is the atomic number. So the atomic mass number is right up here, and that's the number of protons and neutrons that it has in its nucleus. Elements are the simplest forms of substances that compose matter. Every element is made up of only one unique type of atom with an unchanging number of protons. The number of atoms that form a molecule of an element varies, and there are 92 natural elements that we know of in the natural world, but we have almost 24 others that have been created artificially. So when we look at that element chart, you'll see more than 92 on the chart, but a lot of those have been created. The elements that we probably hear the most about are like carbon, oxygen, and chlorine. Those by themselves are just an element. When we start combining them is when they start taking on different energies and different other things. So when we bond something, a molecule is an electrically neutral group of two or more atoms held together by chemical bonds. Two or more atoms bonded together form a molecule. So I said it backwards both ways. A molecule is made out of two or more atoms, electrically neutral. Two or more atoms bonded together form a molecule. Most naturally occurring elements exist independently in nature, and that means it's a pure form, not combined with other elements. So if we start talking about things like iron, zinc, nickel, oxygen, carbon, all of those are pure elements out there. And when we look at anything out there in the world, I don't know where you're sitting right now, but I'm sitting at my desk, and if I look around and I see a pen stuck in my little board, then I think about all the different atoms that were put together to make that compound, to make that pen. A push pen, it's part metal and part plastic. And then I have a picture of my dog sitting here and everything that was put into making that picture. So what we see is the form of chemical compounds because that's what we think about. And I want you to think about right now, what is the most common substance on the Earth's surface? And that is water. And so this is a water molecule. So when we've put these together, this is a hydrogen and an oxygen. So three atoms put together, now we have H, which is hydrogen, the number 2 subscript, which means there's two of them, and one oxygen, that is water. So the superscript number, or subscript is what I said, that appears within it is the mass number, and the subscript is the atomic number. So water is not an element, it's not an atom, it's now a molecule combined of two hydrogens and one oxygen atom. That's the simplest way to go. And then you'll see some others. You'll start recognizing some of the chemicals throughout this whole program, not just this class. You'll learn what barium sulfide is. You will learn a whole bunch of different ones as we go along. Then you need to talk about something called the isos, and it's just a group of terms that all start with the word ISO, and this refers to isotopes, isotones, isobars, and isomers, and it's a way of classifying elemental relationships. An isotope, again, this is something you need to know the definition of. Isotopes have the same number of protons, but different neutrons. An isotone has an element that has the same number of neutrons, but different protons. An isobar, this one's a little trickier, an element whose atoms have a different number of protons, but within the nucleon, the protons and neutrons are the same. So it has the same atomic mass number. And we're talking about when we put these different elements together is when this happens. Then an isomer or an isomer refers to elements whose atoms have the same number of protons and neutrons, but with different amounts of energies within their nuclei. Now, do you need to know exactly what they are? No, but you may actually see the question, what is, and it could be any of those four. So here's your little mnemonic to keep those apart. So look at this one, an isotope. The P is highlighted right there. That means whatever you see highlighted is what is different. So the second to the last letter is, is the characteristic that stays the same. In an isotope, that means the protons are the same. Isotone with an N, neutrons stay the same. This A right here in an isobar reminds you of the atomic mass. So the atomic mass number, A. And then an isomer, the E, reminds you that everything remains the same, but it has different amounts of energy. So you could use it twice here. Everything's the same, but the energy's different. So, there's just something to kind of remember those definitions. That's all you've got to know about it are the definitions. So let's move to the periodic table because that's important too. The periodic table is a way of classifying elements, and it's organized by periods and groups. And if you don't remember that from early science, and when we look at a table in just a second, you'll remember this. So there are 7 periods arranged as rows. Rows go across, and then 8 groups which go down in columns. So the period, all of them have same number of electron shells, and they increase from the top row to the bottom row. The groups going left to right means that they have the same number of electrons in the outermost shell, and they increase from the column from left to right. So that's very important when we look at it, and we'll see them in just a second. Now the table itself is not as uniform as you would think. There are 2 things that are left out, and they don't follow the same rules. There's something called transitional metals, which are in the middle of the chart, and that means that the inner electron shells are being filled, and these elements have some characteristics different from other elements. There are additional elements that don't fit in again, and that's the inner transitional metals. There's 2 series of those. The numbers between 57 and 71, and then 89 to 103 are actually different. And we have some pictures here. This is what's in your book, just so you know that. So if you look, here's 1. All the way out to 114. There's your 57 to 70 and your 89 to 102, which have been put out here. And you need to know these are called lanthanoids and actinoids. So this one's pretty cool, but I like this one a little better. So here is all the groups. So group 1, they all have the same what. Then you have periods, groups go across and periods go down, but then through that they all know what each one of those has, okay? This is a nice color-coded. This is a nice table also because here it's telling you what type of elements there are. So this is a nonmetal, alkaline. Here's your transitionals. There's a lot there. And then there's some of the inner transitionals, which are down into the lanthanide and actinide, or noids, however you want to say that. So, and then this is just a really fun one. So if you went through and look, what's the hydrogen do? Suns and stars. It has you a little picture that you could stop and look at that if you care. My favorite one here is phosphorus, because you're thinking, oh, X-ray. No, it's in our bones. We need it for our bones. And it just, phosphorus is pretty strong. And then there's a couple of these that are not really good for us, radium. Here's some barium that we use in X-ray. So those are kind of cool. Now, one more thing that we need to talk about is bonding. So when we're talking about classification and bonding, we also need to know about these 2 things, ionic bonding and covalent bonding. Now these are just some images of them. This is when you give an electron away, and this is when you share an electron. With ionic bonding, it's based on the attraction of opposing charges. Recall that generally atoms are electrically neutral, and that means they have the same of everything. But when in the presence of other atoms, some atoms have a tendency to give up electrons. And then if they give it up, the other one wants it. So they do that because one is unstable. So in an ionic bond, one of the atom gives it up, the other takes the electron, and then they can now be attracted and bond together. So just like I was saying earlier, if they're the same, they're going to repel. But if he gives one up, and that's what this one did, hey, I'll give you an electron, well now this one's more negative, so now they attract one another. One of the best things to look at here is something called table salt, and that is sodium, Na, and chlorine. And so just one by itself is a chlorine atom, but once you have taken an electron from the sodium, so now it's Na plus because it gave away an electron, so now it's a sodium ion, and then the chlorine has an extra electron, so now it's a chloride ion, and this is sodium chloride. And in case you didn't know that, that is table salt. That's what we put on our food every day. So this is a really cool little picture of how ionic bonding works. Now it's not just two separate elements, it's become a new compound. Then when it goes to covalent, just remember that it's a molecular bond based on two atoms sharing electrons. And so if an electron shell of an atom's fill up, they do so from one of the nearest, from the nucleus outward, and the outermost shells are not always full. So in a covalent bond, think of it as creating a figure 8. So this has one and this has one, but if they come together and share that one, now they're connected. This is what helps us create some complex matter that we're used to. And the bonding of various atoms to form molecules is a common occurrence. So let's look at this one. Here is two hydrogens and one oxygen. Well, they have one, and they want to get together. So they're separate little atoms, but when they come together and share, what do we have? Water. We have water molecules, so that's H2O. And that's a covalent bonding. Now, I have just a really cute slide here just because it was fun. I couldn't help myself. Here's the types of chemical bonds I found on the internet. One is an ionic, and it's cute. Take this and be mine. So he's giving away an electron, and if you do, then now they can be happy and be together. Then this one over here is sharing is caring. So they're both sharing their electrons that they've got sitting on the table. Okay, so if y'all didn't think that one was cute, I did. I'm sorry. All right, that was a quick chapter, but it was also a little bit of fun information. I hope that you actually understood. I kind of talked fast, but what we talked about was atomic theory. Believe it or not, it was simple, short, sweet. We talked about the nature and structure of an atom, the constituents of the atom. Make sure you know what a proton is, a neutron is, an electron is. You need to know about the classifications of the atom and then the way that they bond. That's the most important thing about this chapter. You have some other assignments for the week. I'm not sure when you listen to this, if it's during the same week that you're doing them, and you're going to have a little quiz. So if you have any questions on that, just give me a shout out, okay? I'll be glad to help you any way that we can. And here's just another, I like throwing these x-rays that I have out here. This is of some tulips in the ground. This is really an x-ray, guys, just in case you don't believe me. And I want you to know that so far I'm enjoying it, but I hope to see some of you in some of the other live classes that I may have throughout the quarter. And have a good week, okay? Thanks, and bye-bye.